Hello everyone, my name is Antonio Coleman, and I would like to welcome you to my newest video within my ongoing series where I cover various data structures and algorithms. If this is your first time watching one of my videos in this series, I would highly recommend that you catch up on those videos previously and then come back to this one. However, to recap some of the things that we've covered over the last few videos, these include general background information on BST red-black trees, also things like your self-balancing properties, as well as my previous video where I displayed some code snippets of a project that actually directly works with red-black trees. But in this video, I will take the less hands-on approach and cover an example of how impactful the implementation of BST red-black trees has been on the world around us. Now let's begin. For those who do not remember or simply do not know, the origins behind what we know now today as red-black trees have a very scholarly background. This is because the algorithm was introduced after the 1978 paper titled "The most famous and high-impact implementation of a red-black tree can without a doubt be found inside of the Linux kernel." Here, Linux uses a system called the Completely Fair Scheduler, also known by the acronym CFS, to decide which process gets to use the CPU next in order. If you're wondering how this works, it goes as follows. The scheduler needs to track all the tasks or processes currently waiting for CPU time. It aims to be quote-unquote fair by giving the CPU to the task that has had the least amount of processing time so far. Some advantages of this can include the fact that it allows for the system to store runnable tasks in a red-black tree. Now this, you might ask, why red-black trees? The answer to this is that the scheduler needs to pick the task with the lowest runtime incredibly fast. It also needs to insert new tasks and remove the finished task efficiently. Due to this, the efficiency of red-black trees allows for the O log n time to complete tasks efficiently and in a timely manner due to its time complexity. In regards to more examples, I will take C++, STL, and also Java collections. If you are a programmer, you have likely used red-black trees without even realizing it. This is because they are the engine behind some of the most popular data structures within standard libraries. In C++, the STL or standard template library such as std map, std multimap, and std set are all typically implemented using red-black trees. Additionally, in Java collections frameworks, things like java.util.treemap as well as java.util.treeset rely on this structure as well. If you're wondering how it works because when you create a map to store key value pairs like a dictionary, the language needs a way to keep those keys sorted while also allowing for fast retrieval. If you use things such as a hash map, the data is unordered. However, if you use a sorted array, lookups can be faster, but also adding a new item is slow because you have to shift all the memory. Now, if you're wondering why use red-black trees, this is because they provide the quote-unquote Goldilocks solution. They keep the data stored so that you can iterate through it in order while guaranteeing that insertion, searching, as well as deletion never take longer than the logarithmic time, regardless of the data input. This guarantees worst-case performance, which is essential for mission-critical software. Furthermore, while it may be a little bit more niche, computational geometry also uses red-black trees. This is because when software needs to solve geometric problems, like figuring out if thousands of lines on a microchip overlap, or need to render 3D graphics, they often use quote-unquote sweep-like algorithms. If you're wondering how this works, imagine a vertical line sweeping across a plane filled with line segments. As the line moves, the algorithm needs to track the active segments intersecting the sweep line sorted by their vertical coordinate. If you're wondering why we use red black trees here, it is because as the sweep line moves, the order of segments changes frequently. New segments start, old ones end, and they end up swapping positions. Here, our red black tree handles these dynamic updates dynamically and reliably. They ensure that the graphics engine or CAD software doesn't hang when processing complex geometrics. Now, as that unfortunately completes this video, I would like to thank my references, as linked here, as well as any viewer who comes into contact with this video. I hope you enjoyed, and I'll see you next time.